Our next talker is Matthias from Western Sydney University, so take it away.
Thank you, Kane. So today I'm going to be covering congruence lattices of finite twisted Brauer monoids. To begin with, I'd like to give you a quick overview of what I will be covering today. So we're going to be covering partition monoids, but specifically we're going to look at the Brauer variety. And we're going to look at the more general setting of the twisted variety. This is a little bit tricky to work with, so we're actually going to simplify this a tad to be in a finite setting. We are going to be looking at congruences, so obviously I need to cover what they are. We're going to go through some examples, as well as why they are important. This will then allow me to state the theorem I was able to prove, goes through an outline of the proof, as well as the future directions of this work. And the key takeaway I would like you to have from today is that maths can be done by pictures. So let's begin with partition monoids and specifically their basics. So obviously they are a semigroup, specifically a monoid, and they do have their origins and uses from theoretical physics and representation theory. They come in a number of different flavors, for example, the temporary Lie, Motzkin, Jones, symmetric inverse monoids, and most importantly to us, the Brauer monoid BM. So an element of this Brauer monoid is a Brauer diagram, which is two rows of vertices numbered from left to right, with usually the bottom row being primed numbers. And we have edges in our diagram, or sometimes called blocks. So we might have a non-transversal top block. We might have some non-transversals on the bottom, and we can have some transversals in between the two rows. And a Brauer diagram has got the condition that every vertex must be connected with exactly one other vertex. So we sort of have a pairing up of vertices, if you like. Now, a submonoid of the Brauer monoid is a temporally Lie monoid. And here we have an extra constraint that says that any edges, well, they're not allowed to cross. So our graph must be planar in some sense. We can talk about the degree of a monoid, and this is saying how many vertices have we got. So both of these examples have degree 5. We can also talk about the rank of a diagram. That is just counting how many transversal blocks are there. So in this top example, we have 1, 2, 3 transversal blocks. We have rank 3. The bottom one, we have 1 transversal block, rank 1. We are dealing with a monoid. We need to have a multiplication action, and that's the concatenation operation. Now, for those of you that are visual-based learners, this is an animation of the concatenation process in action. And for everybody else, I'm going to make use of this intermediary step to show you how we end up with the final concatenated diagram. So what exactly are the steps? Well, step 1 is to position the two diagrams one directly on top of each other. And we then add in these red vertical edges between the two diagrams. We're then going to remove the two inner rows of vertices, and we remove any loops. So a loop is any edge that is now not connected to a vertex. So we're going to see we have one loop here, and we're going to have a second loop over here. And this idea of a loop is going to be important for later on. And then we just tidy up with what we have. So we're going to squish our two rows to the normal spacing and draw a nice clean edge for the edges that we have. We can see fairly easily that this operation is going to be associative. It does have an identity diagram, specifically the all vertical edges, and it's not necessarily commutative. That now allows us to get into the twisted variety of these Brauer monoids. And here we need to keep track of those loops that I just introduced to you. So essentially, broadly speaking, our twisted variety is our normal Brauer monoid Cartesian product with the natural numbers, where that natural number just counts how many loops are present in our diagram. Clearly, this is going to be an infinite monoid, and we do need to modify our concatenation process. So if you recall the example I had previously, well, because we're now in the twisted setting, for example, the first diagram, I might say this has got one loop associated with it, and for the second one, it has 3 loops associated to it. And then for our concatenation process, we do exactly the same operation on the diagrams, so that's the same, and then we count up how many loops have we got. So we have 1 from our top diagram, 3 from the bottom, and if you recall, we created 2 loops during the actual diagram concatenation, so 1 plus 3 plus 2 gives us 6 in total. A bit more formally, we have 2 diagrams. When we concatenate them, we do our usual diagram concatenation, and we add up all of the loops from the first diagram, second diagram, and then this map 5, which counts how many are created during the concatenation process. We can also simplify this slightly into a D-twisted Brauer monoid. And this is where instead of Cartesian product with the entire natural numbers, we only go up to D. And for this to remain a monoid, we do need to add a 0 diagram to that. Quite clearly, this is going to be finite now. And the concatenation process here is going to be the 0 diagram trivially, anything with the 0 diagram, but also if the number of loops exceeds our number D, essentially the max number of loops that are permitted. A special case of this is when D is equal to 0, in which case our 0 twisted Brauer monoid is just the ordinary Brauer monoid with the addition of this 0 diagram. And in terms of concatenation, well, as soon as any loop is created, we have the 0 diagram. That brings me to the congruences. So what exactly are they? Well, it's an equivalence relation, usually denoted by sigma on the set of diagrams. But it must be compatible with concatenation. Specifically, that means if I have a diagram of alpha and a beta that are congruent, if I concatenate on the right with any other diagram, say a gamma, that must still be congruent as well. And likewise, I want the same condition to be on the left. Some easy examples are the universal congruence, where everything is congruent with everything else, and likewise the trivial congruence, where everything is only congruent to itself. We can see that we're going to get a lattice with subset inclusion between these. So, for example, we would have our trivial congruence at the bottom, we'd work our way up to the universal congruence at the top, and in between we might have all sorts of other congruences with various relations and strict subsets between them. Now, if I were to do this for an arbitrary semigroup, generally speaking, this congruence lattice is going to be very complicated and basically of no use. But it's a remarkable fact that for partition monoids, these congruence lattices are very simple, and at times they are as simple as just a chain. Another congruence we're going to need are the principal congruences. And this is where we take an alpha and a beta and we define them to be congruent. And we essentially say, well, what's the smallest congruence that contains those 2 diagrams? Why are congruences important? Well, because they govern quotients in exactly the same way that ideals are important for rings or normal subgroups are important for groups. Before I continue, we need to take a quick dive into some semigroup theory. Specifically, we're going to need to understand Green's relations. Again, these are an equivalence class on the set of diagrams. And the first one we're going to cover is the R relation. And this says if we have 2 diagrams, if their top rows are the same, then they are R related. What do I mean by the same? Well, that means if a vertex is part of a transversal block, it has to be a transversal block in the other diagram. So we can see we have 2 transversals, and then 2 non-transversals, 2 non-transversals. Now it's important to note here this is a not example. Even though all 4 of the vertices are part of non-transversal blocks, the actual non-transversal blocks need to match up exactly, which clearly in this case they don't, hence they are not R-related. In an analogous fashion, we have the L relation, where instead of looking at the top row, we want the bottom row to be the same. We can take the intersection of these 2, that's the H relation, and that would obviously mean that both the top and the bottom row have to be the same. And there is a bijection between a H class and the symmetric group of that rank, which you can already see here that I have rank 2 and I have the symmetric 2 group popping out here. And this bijection is going to be important to keep in mind for later on. Instead of taking the intersection, I can take the join. That's going to give me the D relation. And for diagrams, 2 diagrams are D related if they have the same rank. You're probably familiar with the notion of an ideal subset where if we multiply on the right or left, we stay within the subset. And for diagrams, we have a nice easy expression for the ideals. They are all the diagrams of a given rank or less. One final ingredient we're going to need is a hat map. This is defined from even degree. And essentially, this just annihilates any transversal blocks in the most obvious way and just makes them non-transversals. That now allows me to state the congruences we're going to need. So to understand this, I'm going to make use of an X-box diagram. And the reason I have an asterisk here is because this is an entirely made-up example. So at the bottom, we would have a single element, our 0 diagram, and then we would have our D classes. So D0, all diagrams of rank 0, D2, D4, and here we're only going up to degree 6. Now, 2 diagrams, if they are in the same row, they're going to be R related. And likewise, if they're in the same column, they're going to be L related. Obviously, that means if they're exactly in the same box, they're going to be H related. So you can sort of think of this being full of little tiny dots, each dot representing a diagram. First up, we have the Rees congruences. And this is where we take everything to be trivially congruent, and the P ideal is identified together. So if we say, look at the R2 relation, that means everything in the second ideal, so of rank 2 or less, everything in this red box gets identified as a single element. We then have some group-based congruences, and this is where we take the Rees congruence of the rank beneath, and we go for the rank we're looking at if we are H-related, which, if you recall, gives us a bijection to groups. If we then also have some group action, we are congruent. Now, I'm not going to go into details what that group action is all about. But as an example, if we're looking at the alternating 4 group, well, we have our Rees 2 congruence, so everything in the second ideal is identified together. And then in our rank 4, within a H class, each diagram is either going to be an odd or an even diagram. So we say have all the odds in blue and all the evens in yellow. And this is going to get repeated across each of the H classes, but those are different. So we have different colors across the H classes. We can also look at the symmetric 4 group, where again, we have our second ideal being identified together, but this time the group action is much more broad, where everything in the H class satisfies the group action condition. So the entire H class gets collapsed to a single element in the rank 4 case. Next, we have a collection of congruences, first lambda up. This is where we started with the symmetric 2 group congruence, and we add on a possibility that if they are related and have the same hat, that they are also congruent. So this is our RS2, everything in the 0 ideal gets identified, and everything in rank 2, the H classes get identified together. But then we have the additional option that if things are R-related, so within the same row, if their hats are the same, they're also identified. So that may be that some H classes get identified with other H classes in the same row. And obviously this is repeated across each of the different rows. In very much analogous way, we have lambda down. This is where we replace the R relation with the L relation, which means instead of having H classes identified across rows, they're now identified across columns. And we can sort of put these together to get the lambda congruence, where we just drop this R or L condition altogether. We just need their hats to be the same. And if you do the calculation, this is actually the join of these previous 2 lambda congruences. What does this look like? Well, instead of needing to be within the same row or the same column to have H classes identified, they may fairly arbitrarily be identified together, obviously as long as we have the same hat. And finally, we have some new congruences. So mu S2, where we take the trivial congruence, and if we're of rank 2, we have a group action. And in this case, this is the same as simply being H related. So that means if we're in rank 2, we have all of our H classes being collapsed together. And finally, the most complicated one, mu Klein 4. This is where we take lambda as our starting point. That takes care of rank 2 and less. And then for rank 4, if we're H related and have the Klein 4 group action, then we're also congruent. So if you recall, this is our lambda congruence, which takes care up to rank 2. And then if we are H related, well, we can be one of the 4 Klein elements. So each H classes are split off into 4 different groups. And again, this gets repeated across each of the H classes. Now that is quite the mouthful to get through. So I'm actually going to go through all of these again, but in a much more pictorial fashion. So let's begin with some diagram. If I have the same diagram, well then those 2 diagrams are going to be trivially congruent. Now if I have these 2 diagrams, we can see they're of rank 2 and they're H related. That means they're going to be part of mu S2. But clearly we have a strict subset because these are 2 different diagrams, so they're not trivially congruent. Now I'm going to need a second row, so I'm just going to copy my first diagrams. And to remind ourselves of this, I'm going to put an equal sign there. Now these 2 diagrams are of rank 0, they're not the same. So we can see they are going to be a part of R0, but clearly not part of the trivial congruence. And we can also see that these 2 diagrams are of rank 2, so they're not going to be related under R0. And likewise, these are of rank 0, so they're not going to be related under mu S2. We do not have equality here. We can keep building this up to include the symmetric 2 group congruence. This 2 diagrams are of rank 0. Everything in rank 0 is included in here. But again, rank 0 as we had here is not included in mu S2. And likewise, again, RS2, these are H related. We can see the symmetric 2 group here. They are RS2, but because they are of rank 2, they are not included in R0. Continuing up, we have our lambda up, which recall we need to be R related. Top row is the same, yes, and hats need to be the same, yes. But these 2 are clearly not H related, so they're not part of RS2. And in a similar fashion, lambda down, bottom row is the same, yes, and hats the same, but again, not H related, not a part of RS2. And we can easily see that lambda up and lambda down are different because here we're not L related, and here we are not R related as would be required. But they are a part of the lambda congruence, where we just need to have the hats be the same, which is the case. But these 2 diagrams are not R related, so they cannot be a part of lambda up. Similarly, here, these 2 diagrams are not L related, so they cannot be a part of lambda down. Next, we have mu K4. So this is a diagram of rank 4. We have the Klein group here. Yes, we're part of mu K4, but rank 4 is not congruent in lambda. And R2, this is an arbitrary rank 2 diagrams. Only diagrams that have the same hat are related in lambda. So we have a strict inequality here. And we can see these are different. This is rank 4. This is only rank 2. They are not congruent in each other. And finally, we have RK4. So this is where any rank 2 diagrams identified together, yes, but these 2 would not be identified here because we would need the hats to be the same. And likewise, this is of rank 4, so it is included in RK4, but rank 4 is not included in R2. That now allows me to state my theorem. So the theorem I was able to prove this year is that for the zero-twisted Brauer monoid, the congruences that I just went through with you, those are in fact all of the congruences of this monoid. And the congruence lattice is, well, in the odd degree, a simple chain working your way through the Rees and group-based congruences. In the even case, it's a little bit more complicated. We sort of have three diamonds at the bottom. The strict inclusions of that I already went through with you in the previous slides, and we have the same tail as we do for the odd degree. In terms of a proof for this theorem, well, step one is to obviously show that all these congruences that I say are congruences are in fact congruences. And then I need to consider every single pair of alpha and beta and look at the principal congruence generated from those. I need to show that that principal congruence is contained in my list. I then need to show that this list is closed under joins, which obviously for odd degree is trivial, and even for even degree is pretty straightforward. And then I'm able to employ a very powerful lemma by East, Ruškuc, and Tolpe, which essentially says, if we have these above conditions satisfied, then the list of congruences I have is in fact the entire congruences of the monoid. To give you a bit of a better understanding as to how to check all of the different congruences, this is the decision tree I went through. So we begin with some diagram alpha and beta, and we look, are they the same diagram or are they different? Is one of the diagrams the zero diagram, or are both diagrams non-zero? Are the diagrams of different rank, or have they got the same rank? We then look at, are they R related? And if not, exactly why not? We then split off into odd and even degrees, and we pick out, are we H related or not? And then we need to take care of some low order, the low ranks specifically, as well as the client for action as a special case. That brings me to the end of my talk. So I've introduced you to partition monoids, specifically the twisted Brauer variety. And I went through congruences and showed you some examples. This allowed me to state what the congruence lattice is for the zero twisted Brauer monoid. And the next steps for this line of research would be as follows. So obviously the setting we were working in was d equaling to 0. It would be nice to generalize this to an arbitrary value of d. And also, if you recall, that was the finite version. It would be nice to go back to the larger infinite twisted version. That would conclude the Brauer monoid. And next would be to pick another monoid and do the same analysis. Most likely the temporary leave is the obvious choice, considering it is a submonoid of the Brauer. Hopefully by now you have learned that maths with diagrams is possible and can be quite enjoyable. Are there any questions?
Thank you for the talk. Does anyone have any questions? I guess my question is, with these next steps, do you have any sort of expectations of, like, is it going to be kind of the same deal with your proofs, or is it going to be like a much more challenging sort of generalization if you were to say increase D or go to the infinite twisted case?
Sure. So all of these have been done for the straight partition monoid, and in that, the level of difficulty and sort of complexity increases quite substantially to these other cases. And the proof methods for those are actually sort of in the reverse order. They consider the infinite case first, and then sort of pull out a finite D as sort of a special case of that. And then as a special subcase of that, they pull out D equals 0.
Okay. And you said you used the powerful lemma by East and a few others. Was that previously used for other sort of proof of something, or is this the sort of the first time it's being kind of applied somewhere?
No, this lemma, I believe, was basically created for establishing these congruence lattices, and that's sort of how they were able to prove the first congruence lattice results. And obviously, I'm just using it because, yeah, it is very useful.
Yeah. Okay, cool. If no one has any other questions, let's thank Matthias again.